Welcome back to Java Internals Crashcasts. I'm your host Sheila, and today we're diving into a crucial aspect of concurrent programming, contention, and coherence. We're currently in our advanced topics season, exploring the chapter on performance and scalability. Victor, are you ready to unravel this complex topic for our listeners?
Absolutely, Sheila. I'm excited to break down these concepts and help our listeners understand how they impact the performance of concurrent Java applications.
Great. Before we dive in, let's start with a quiz question for our listeners. Here's a brain teaser. In a multi-threaded application, you double the number of threads performing the same task, but the overall performance only improves by 20%. What might be the primary cause of this sublinear speed-up?
Ooh, that's an intriguing question, Sheila. It really gets to the heart of what we're discussing today. Without giving away the answer, I think our listeners will need to consider how threads interact with shared resources. It's a situation many developers might encounter in real-world scenarios.
Absolutely, Victor. Now let's start with the basics. Can you explain what we mean by contention in the context of concurrent programming?
Sure thing, Sheila. In concurrent programming, contention is like a traffic jam for computer processes. It happens when multiple threads, think of them as cars, try to use the same resource at the same time. This resource could be processing power, memory, or access to shared data. When threads compete for these resources, it can slow things down, just like too many cars trying to merge into one lane.
That's a great analogy, Victor. It really helps visualize the concept. So, how does coherence fit into this picture?
Well, Sheila, if contention is about traffic jams, coherence is about making sure everyone has the same map. In computer terms, it's about keeping data consistent across different parts of the system. Imagine each core in a multi-core processor has its own little notebook. Coherence ensures that when one notebook gets updated, all the others get the memo too.
I see. So it's like keeping everyone on the same page, literally. Can you give us an example of how this might play out in a Java application?
Certainly. Let's say we have a shared counter in our program, like tracking the number of items in stock. Different parts of the program might be checking or updating this number at the same time. Coherence makes sure that no matter which part of the program looks at the counter, it sees the most up-to-date value.
That makes sense. Now, I'm starting to see how this relates to performance. If we're constantly updating and checking these shared values, it could slow things down, right?
Exactly right, Sheila. This is where the performance implications come in. Both contention and the need for coherence can significantly impact how well our programs run, especially as we try to do more things at once. Let's dive a bit deeper into some specific issues and strategies to address them.
That sounds great, Victor. Can you tell us about some common types of contention we might encounter?
Sure, one common issue is lock contention. It's like when multiple people try to use the same bathroom. Only one can go in at a time, and the rest have to wait. Another tricky problem is called false sharing. Imagine if changing your grocery list accidentally updated your neighbor's list too, just because they're stored close together. That's kind of what happens with false sharing in computer memory.
False sharing sounds tricky indeed. How can developers identify and avoid it?
Good question. False sharing can be sneaky, but there are tools like Java Flight Recorder that can help spot it. To avoid it, developers can use techniques like padding, essentially adding extra space between variables in memory. There's also a special annotation in Java 8, and later called rcontended, that tells the system to keep certain data separate.
That's fascinating. Now, you mentioned cache coherence protocols earlier. Can you break that down for us?
Of course. Think of cache coherence protocols as the rulebook for how different parts of the computer share information. One common protocol is called messy. It's like a system of traffic lights, telling each part of the computer when it's okay to read or write data, and when they need to wait or update their information.
It sounds like managing all of this could really affect how well our programs run. What strategies can developers use to minimize these issues?
Great point, Sheila. There are several strategies developers can employ. 1. Minimize shared changeable data. The less information different parts of the program need to share, the better. 2. Use special collections designed for concurrent use. Java has some built-in tools for this, like concurrent hash map. 3. Use smaller, more specific locks. Instead of locking a whole database, just lock the specific record you're working on. 4. Try lock-free approaches. Sometimes you can use special operations that don't need locks at all. 5. Divide and conquer. Split your data and tasks so different threads work on separate pieces.
Those are great tips, Victor. Can you give us a real-world example of how contention might show up in a big application?
Certainly. Imagine a popular online store during a big sale. If the system keeps track of how many of a hot item are left using a single counter, you might see major slowdowns. Thousands of people trying to check or update that one number at the same time could cause big problems. It's like thousands of people trying to look at and update a single price tag in a store. Chaos.
That's a vivid example, Victor. It really shows why understanding these concepts is so important. Now, before we wrap up, let's reveal the answer to our quiz question. Victor, would you like to do the honors?
Absolutely, Sheila. The likely cause of the sublinear speedup in our quiz scenario is contention. When we double the number of threads, we're also potentially doubling the competition for shared resources. This increased contention can offset some of the performance gains we'd expect from parallel execution, resulting in the modest 20% improvement we saw in the question.
Thank you, Victor. To summarize today's episode. 1. Contention occurs when multiple threads compete for shared resources. 2. Coherence ensures consistent views of shared data across multiple caches. 3. Both contention and coherence management can significantly impact performance. 4. Strategies like minimizing shared state, using concurrent collections, and employing fine-grained locking can help mitigate these issues. 5. Real-world scenarios like high-traffic websites can face significant contention challenges. In our next episode, we'll be discussing benchmarking concurrent code, which will build on the concepts we've covered today. Don't forget to subscribe to Java Internals Crashcasts and leave us a rating if you've enjoyed this episode. Until next time, happy coding!